All right, well, in this video, we are going to talk about the nuts and bolts of doing a kinetic analysis. When we do a kinetic analysis, we're really using Newton's three laws of motion: uniform motion, law of acceleration, and law of action reaction. To use Newton's second law, we only identify the forces acting on the object, not by the object. Newton's third law tells us for every force acting on the object, there's an equal and opposite force created by the object, or vice versa. But what we're going to practice is identifying only the forces acting on the object. And then we put those forces into the equation, sum of forces equals ma. All right, so let's go through it. I'm going to switch over to a different camera. All right, kinetic analysis. Identify only the forces acting on the object, because eventually we're going to use F equals ma:/com. Sum of forces acting on the object equals mass times acceleration of the center of mass of the object. All right, so let's look at this a little bit more. Let's remember that forces are represented by arrows, okay? And an arrow will have a length, and that length represents the magnitude of the force. The longer the arrow, the bigger the magnitude. So when we do our kinetic analysis, it's nice to try to draw an arrow that represents what we think is the magnitude of the force. Okay, the other part of the arrow is it associates a direction with the force. So obviously the direction of the arrowhead tells us which way that force is acting. And then we also have what's called the line of application of force. This is a straight line projection in both directions of the force. Okay, so the final characteristic of drawing a force vector is point of application, where that force is acting on the object, if this is the object. Obviously, where we draw the arrowhead pushing on the object, that ends up being the point of application. Okay, so let's do some practice. The first practice that's good to do is just a projectile. And remember, a projectile is anything that's thrown up in the air and it's not touching the ground or anything else in the air. So I'll just draw a circle, and I've drawn two forces acting on the object: the force of gravity and the force of air resistance. Now this presumes that the ball or the object is headed in that direction. All right, why? Because the air resistance force is going to oppose the direction of movement. All right, so I only identify forces acting on the object, not by the object. So over here, I've written by. For each of these forces acting on the object, there's an equal and opposite force, but we're not going to do the by forces. The by force is the ball is pushing on the air and the ball is pulling up on the ground. Okay, but we don't need to know those forces. We don't need to concern ourselves with the forces, because what we need to do in a kinetic analysis is identify only the forces acting on the object and then put those forces into this equation. Sum of forces acting on the object equals mass times the acceleration of the center of mass of the object. Okay, so this is our main kinetic equation that we're going to do. So projectile motion, two forces acting on the object: force of gravity and force of air resistance, or drag force. Okay, we add those two up and we get mass times acceleration. If those two forces are equal to each other, they're opposite direction, that would give us a zero acceleration, constant velocity. If the force of gravity is greater than the air resistance, then we would have some acceleration. If the air resistance is greater than the force of gravity, we would have acceleration as well. So we would just add up those forces to get the acceleration of the object. All right, let's go through another. Sometimes what I like to do is just start with a projectile with no air resistance. Okay, and then we only have one force acting on the object, the force of gravity. And we know if the force of gravity is the only force acting on the object, that the object will undergo an acceleration of negative 9.8 meters per second squared. So let's just look at it from an equation perspective. Some of the forces acting on the object equals ma, mass times acceleration of the center mass. If this is the only force acting on it, I'm going to assign a negative sign there because it's a downward, and up is typically considered positive. And the force of gravity is going to equal to the product of mass of the object and the acceleration of the center mass of the object. And therefore, force of gravity equals mass times negative 9.8 meters per second squared. So this is the acceleration due to the force of gravity, negative 9.8 meters per second squared. It's the acceleration due to the force of gravity. One of my pet peeves is when people say gravity is negative 9.8 meters per second squared. That is incorrect. Gravity is a force. This is the force. And the force is equal to the magnitude of the mass times the magnitude of the acceleration. And what's odd about gravity is that if we drop all objects, any object, when gravity is the only force acting on the object, we'll get an acceleration of negative 9.8 meters per second squared. Okay. All right, so let's keep going. If we have air resistance, I've already drawn that on the previous page. Then we have force of gravity pulling down on the object and the air resistance pushing up on the object. And we get this equation. Knowing F equals ma, sum of forces acting on the object equals mass times acceleration. So we get positive air pushing up on the object, negative force due to gravity, because it's pulling down on the object. We add those two up and we get the product of mass times acceleration. And this should be COM here too. All right, so if one force is greater than the other, that's gonna drive an acceleration in a particular direction. If this force is greater than that, we're gonna drive that acceleration. If you do skydiving, you may have heard the term terminal velocity. What terminal velocity means is if you jump out of an airplane, you will start to speed up moving downwards. That's a negative acceleration. That means the force of gravity is greater than the air resistance. But at some point, the air resistance gets to be the same magnitude as the force of gravity. And when that happens, these two add up to zero acceleration. That means constant velocity. That's terminal velocity. All right. Let's do this one here. I'll cover up this part for now and just talk about this part. So we just got an object sitting on a table with no movement. Identify the forces acting on the object. We've got the force of gravity pulling down on the object, and we've got a new force here pushing up on the object. That's the ground reaction force. Okay, that's the ground reaction force. When the ground is pushing on the object. That's the force of the table pushing on, I called it the eraser here, because I often use an eraser in class. So if we need to know the acceleration of the object, we put those two forces into the equation of sum of the forces acting on the object equals ma. And here I've specified vertical direction. And as long as the object's not moving, I know the force of gravity pulling down on the object is the same as the force of the ground pushing up on the object. Well, that's why you stand still on a bathroom scale. You stand still on the bathroom scale so that gravity is the same magnitude as the ground reaction force, and you get zero acceleration. I'll go through that again later on when we do some more kinetic analysis of movements. But if I'm interested in another direction, for example, horizontal motion, okay, I would have to add up any horizontal forces acting on the object to understand the acceleration in the horizontal direction. The way I've drawn this right now, I don't have any horizontal forces. So I'm going to skip over that at this point and let me do the next cartoon. So here, what I've tried to draw, this isn't very good, is I've got my reference frame, X and Y. That's my global reference frame. I've got my eraser, my box, whatever. And now this is supposed to be a hand pushing on the box. So like this. Okay, that's what it's supposed to, that's my bad drawing. So what's a kinetic analysis? We identify forces acting on the object, not by the object. And the forces acting on the object include the finger pushing on the eraser. And as I push on this box, which could be similar to the eraser, there's also a force pushing back on the eraser from the table, trying to slow that eraser down. That's friction, okay? That's friction. So there's another force over here pushing on the object. I also have the weight vector, gravity, pulling down on the object, and then I also have a force vector right here, the ground reaction force, pushing up on the object. So once I identify all the forces acting on the object, I pick a dimension to analyze. Maybe I'm interested in the horizontal movement, maybe I'm interested in the vertical movement. Then I take those forces in that direction and put them in the equation, sum of forces equals ma. All right, so that's what I have broken out here. If I'm interested, for whatever reason, in the vertical movement of this object, again, you're looking at this top down, but the vertical movement, there's no vertical movement of this object, even if I'm pushing on it and moving it. But if I am interested in the vertical movement, I would add up all the forces acting on the object in the vertical direction. And that would equal the product of mass of the object and the acceleration of the center mass in the vertical direction. What's the acceleration of this object in the vertical direction? Again, you're looking at it from the top side. It's 0. Why is it 0? Because velocity is constant. And in this case, velocity is constant and 0. So there's no movement in the vertical direction. So it's not very exciting, but this is what I would have for my equation. Negative force of gravity, because that's pulling downwards and up is positive, plus the ground reaction force pushing up on the table, that equals MACOM, mass times the acceleration of the center mass. So as long as these two forces are equal in magnitude, acceleration is 0, which is constant velocity. And in this case, velocity is 0 meters per second, meaning no movement. And it's still no movement, and still no movement, and still no movement in the vertical direction. So constant velocity, 0 acceleration. Now, if we are interested in the horizontal movement, how this object is moving across the table, well, now I look at forces in the horizontal dimension. And what forces do I have acting on the object? They're going to add up to the product of mass times acceleration in the horizontal direction. So I have the push force. Now, why is it negative? Because here's my x-axis right here. And the way I've drawn my origin, that means movement in that direction would be positive. So with the arrow pointing this way, that's a negative force. And this force of friction is going to be positive, given my reference frame that I've set up. Okay, so I have negative force of the finger pushing on the eraser or on this box, plus force due to friction equals MACOM. Okay, so now what's really important is that these two forces do not need to be equal and opposite. They do not, okay? They do not. If I'm pushing on the box here, the force of friction does not need to be equal and opposite to the force that I'm pushing. That's Newton's third law states for every force acting on the object, there's an equal and opposite force created by the object. Two different things, okay? We are only going to identify forces acting on the object. We are not going to identify forces created by the object. These two forces do not need to be equal to each other. Why? Or how can I demonstrate that? Well, if I can speed up on this object, that means that those two forces, force of friction and the pushing force, are not equal to each other. Why? Because I had some acceleration. I had some change in velocity. I had a rate of change of velocity, and I sped up. And so that would mean that the pushing force would be greater than the friction force, and therefore I would have a negative acceleration. And given the way I've drawn that picture, that negative acceleration for this situation is going to mean speeding up, moving in the negative direction. All right, so it would be velocity starting here is 0. The way I've drawn my figure, and this is time, I would have speeding up while moving in the negative direction. That's a negative acceleration. That means that this force is greater than this force. So I'd have to make this arrow longer. So the magnitude is greater than that. That means the object's going to speed up while moving in that direction. Right now, if I take away that force, I release the object. Well, now I've only got the force of friction pushing on the object in that direction. That means that force is going to cause that object to slow down while moving in the negative direction. Okay, but the key here is we're doing a kinetic analysis, and we want to identify forces acting on the object. And then we put those forces into the equation. Forces acting on the object, we add them all up, and that equals the product of mass times acceleration of the center mass. Okay, so this is boxes, but we will do a kinetic analysis of other sports as we continue. Okay, thanks everybody.